So, hello everyone, and welcome to this weekly online session that we conduct, Ask AuxEn Anything. And as you all know, that this is an online platform for uh, civil structural engineers to interact with us and ask their doubts or queries that they may have related to RCC, steel design, composite design, or any project that they are doing, or construction and site related queries. So this is the 79th such episode, such session that we are conducting. And let us begin today's session by taking the queries that have been asked. So first I shall take the queries from the Google form that have been put on the Google form, and then we will go to the live audience. Okay. So let me just share my screen. I hope you can listen to my voice. Right. So let us begin by taking the first question for this session. And the first question has been asked by Engineer Pratham Maskara. He is a working professional from Kolkata, and he is asking, could you please explain cracked and uncracked RCC structural design? What type of design we should use, cracked or uncracked, for practical construction, and how to tell the software that we want cracked or uncracked design. So in RCC design, let's talk about this in two parts. So one will be, let's say, your ultimate calculations. Okay, now cracking, when will cracking happen? When concrete is subjected to tension. And when is concrete subjected to tension? So concrete will be subjected to tension under flexural moments or under flexural action, or when there is axial tension. Okay. Now, if this was my cross section, let's say, and moment was sagging in nature, then tension is at the bottom. So usually, how do we consider the cracked concrete in our calculations? Tell me. So if this was your neutral axis, how do we consider cracking of concrete in our uh, ultimate at the ultimate limit state? How do we consider it? So at ultimate limit state, we consider cracking by ignoring the entire concrete which is in tension. Okay. So if the moment was sagging, I'll ignore this completely, ignore this concrete in all my calculations. If it's an ultimate limit state of tension, okay, if it's an ultimate limit state, and so this, how is software able to understand this? Because the flexural formulae that we calculate, those are built on this particular assumption that concrete in tension will be totally ignored. Although the concrete in tension cracks at, let's say, if I were to write down, concrete in tension cracks at the rupture strength. What is the rupture strength as per IS code? 0.7 under root FCK. Am I right? Just I'm unable to recall. Is it 0.7 under root FCK? Rupture strength as per Indian code. As per American code, I think rupture strength is 0.62 under root FC dash, if I am able to recall correctly. So when I'm talking about concrete in tension, wherever the tensile stresses go beyond this value, that portion of concrete is cracked. But for our simplicity of calculations, we ignore the entire concrete which is in tension. And how does the software consider it? So all the flexural formulae that are based in the software, for design, those are based on this assumption that it will fully ignore the concrete in tension. Now, if you have ultimate limit state of tension itself, that means right now we had the ultimate limit state of flexure. If you have the ultimate limit state of tension, then the entire concrete in cross section will be ignored and all the tension will be taken by reinforcement alone. Understood? So this is the ultimate limit state of tension. In ultimate limit state of compression, we are not considering cracked concrete because it's under compression. Compression does not lead to cracking. So when it's ultimate limit state of compression, we will consider concrete in our cross sectional calculations. When it is the limit state of shear, when we are discussing ultimate limit state of shear, for shear calculations, it depends on the confinement that is being provided by the reinforcement. Okay, so if you look at the IS 456 design, we do consider concrete strength to a certain extent. But if you are doing the IS 13920 based design for shear, I don't know if you know it or not, but if you look at the IS 13920 design for shear in beams, then even in columns shear design, it tells you to take VC as 0. So it's saying that because concrete has cracked under the effect of reversible forces, EQ forces, so do not consider concrete in shear to be effective, and so we take VC as 0 and all the shear is supposed to be taken by stirrups. So this is how we are this is how we are considering the effect of crack in our structural design at the ultimate limit state. Now, if you want to understand the effect of cracking, how it is considered for the serviceability limit state, what do we do? So for deflection, usually what we do is we do the calculations for elastic uncracked sections, isn't it? By default, if you are doing any analysis in your software like ETABS or SAFE or STAT, usually it is as a default setting, it is doing the calculations considering the section to be elastic. That means material level, it is considering elastic and uncracked. So because of that, all the calculations that happen, let's say this was a case of beam, all the calculations that happen for a uncracked section, and if it is considering uncracked section, it takes the gross moment of inertia. That means the entire section, it will do the let's say BD cube by 12 plus plus the effect of reinforcement is considered. So it is basically doing the calculations as per the gross moment of inertia. Now this calculation is not accurate because your section is cracked, and you should not consider gross moment of inertia, but you are supposed to consider what is called as the effective moment of inertia. Now those calculations are slightly complicated. So what your code tells you generally for for deflection, vertical deflection, is that you ensure a certain minimum L by D ratio is appropriately taken for your member, whether it's a beam member or a slab member. And if you are ensuring that you have taken a certain minimum L by D ratio, then you can assume that the vertical deflection check will be satisfied. Okay, that is what your code is trying to tell you. Now, if you do not do that, if you don't want to take the L by D ratio minimum requirement as per the code, then you have to do the calculation for deflection. Then your code says that you then do the calculation for deflection, and then you are supposed to take the effective moment of inertia, and effective moment of inertia will be calculated on the extent of cracking. So then what is your service level moment, that you have to find out how much more or how much it is as compared to your cracked moment, that you have to find out. Accordingly, you will have to find out the effective moment of inertia, and then this effective moment of inertia is supposed to be used in your deflection calculations when you need to consider the I. So your, for example, American code gives you a proper step-by-step approach for this. So if you look at IS 31825, I think chapter 24 gives you all these calculations, that if you want to calculate the vertical deflection, how to properly do it. Okay. Is my voice audible? Please tell me yes, no. Okay, yeah. Now, if you have to consider the lateral deformations of your structure, so this I was talking about the vertical deflection. Now, if you have to consider the lateral deflection of your structure, and mainly I'm talking about lateral deflection due to EQ effects, then how do you consider the effect of cracking in your sections? Can someone tell me how do you consider the effect of cracking in your sections if you want to calculate lateral deflection or lateral drifts, let's say, when subjected to EQ forces? Then you have the concept of modifiers. Okay, so what we are given the stiffness modifiers to calculate the lateral deflections due to EQ effects. Now, I must add over here that these modifiers we use for our normal gravity analysis also, used in gravity analysis also. Okay, in gravity analysis they won't make much of change, so to say, but the real requirement of using modifiers, stiffness modifiers, is to consider the, or is to calculate the lateral deflections under EQ forces. So stiffness modifiers are doing the same job, that they are reducing the cross section, because some of the cross sectional elements, because some portion of the cross section is unavailable due to crack. Okay, so this is how the cracking thing is considered in our entire design process. So what did I tell you? If you are talking about the ultimate limit states, then I explained you how cracks, how the effect of cracking is considered. In service limit state, for vertical deflection, I told you how cracking is considered, and for lateral, I explained how cracking is considered. So I hope this explains, or this answers your query. Very good question, I would say, uh, because this is a question that is common to many of the people. I mean, it is a common doubt that many of us have. So good that you asked. Next question is from Engineer Shubham Desai. He is a postgraduate student. He is pursuing his post graduation from Mumbai, and he has put this question. Image has been sent through email. Let me see email. Is my voice audible? I'm not sure because I'm not getting any feedback. So I don't know if my voice is properly audible or not. So if someone can just type in yes, no, whatever. So this is the image that has been sent. Yeah, this is the image that he has sent. So what he is asking in this case, what is the effect on the axial force transfer of the columns as the eccentricity is produced in the center line? Also, bending moment behavior in the columns would be the same, or it may get changed. Yeah, so behavior may get changed because now there is a eccentricity that is being generated. So your column center line was here for the up. So for example, you are doing column reductions. Let's say this green was the column size at the lower stories. Then at upper stories, let's say you decided to slightly reduce the size, keeping the side face same. So now this red thing is the column size, maybe for some upper levels, and at the upper levels again you decided to change the size. So this black thing is the, all these are plan views. So this is the black is the column size above for the upper story. So now you can see that the column center lines are sort of shifting, and the question being asked is that due to axial load, or let's say the action of axial load now will be at certain eccentricity. Okay, so how to consider that effect? So a software like in software like ETABS, what you can do is that there are insertion point, option of insertion point is there, option of insertion point. So that option you can use, insertion point option. So through insertion point option you can tell the software that where that column has to be placed. So maybe you can do the insertion with respect to this point, side point. Okay, because this point that I have marked, let's say point A, this will remain concentric for all the columns till the bottom story, let's say. So I can mark the insertion point in a software like ETAS over here. So all columns will be placed with respect to this point. Automatically the eccentricity will be developed, and then to include that eccentricity you can use something what is called as a rigid link. So this rigid link, you can model it as a link element, as a horizontal element like this. And similarly for the bottom floors, you will have a rigid link like this. Basically in elevational view, it will look something like this, that from here I have a rigid link, and from this center to this center I have modeled a rigid link like this. Now this rigid link will, without showing any bending behavior, it will transfer the axial forces, and it will also transfer the effects of eccentricity of those axial forces to the columns below. So this thing you can do in the software. Manually if you want to check, then you can just take the axial load and try to multiply it by the eccentricity and see how much moment it generates. Okay, is it clear? Yeah, so this is how you can include these effects. Good. The next question is from engineer Manish Kumar Pandey. He's a working professional from Ranchi, and he's saying, please explain the clause. Please explain the clause 13.4.6.7 of ACI 31825. Please explain the clause. What explanation do you need? Let me try to open the code. I'll just open the code. Wait. 13 point. So chapter 13 is related to foundations. 13.4.6.7. So it's a clause on pile caps. So this is the clause from ACI 31825. Calculation of factored shear on any section through pile cap. Entire reaction from any pile with its center located d by 2 or more outside the section shall be considered as producing shear on that section. Entire reaction. So let's say if this is my pile cap, green thing is the pile cap, and red items are my piles. Okay, I have tried to draw a 4 pile cap. Entire reaction from any pile with its center located d by 2 or more outside the section. Okay, so for example, if this is my section, okay, this is XX section. Over here I want to calculate the shear on this section. So entire reaction from any pile with its center located d by 2 or more outside the section shall be considered as producing. Okay, so if this distance is more than this is phi, so if distance is more than phi by 2, that means half the pile dia. Okay, then you consider whatever is the reaction on this pile. Let's say the pile reaction is P, then that entire reaction is assumed to be creating shear on this section XX. Is it clear what I just said? Okay. Okay. Then reaction from any pile with its center located d by 2 or more inside the section shall be considered as producing no shear. Acha, okay. So this is d by 2 or more inside. This was d by 2 or more outside. Actually, they should have written d by 2 or less. Anyway, so for example, if I consider a section over here, this is my section, let's say x2, x2, and this is my pile center. Now, if this distance is less than phi by 2, where phi is the pile dia, then I will not consider any shear on this particular section. Okay, so the reaction from the pile, the reaction that is acting on this pile P2, I'll not consider this reaction on this pile P2 to be producing any shear on this section x2, x2, which is at a center, which is at a distance less than d by 2. Is it clear, Mr. Manish? This is simple clause, just like we have in our IS code or any code for that matter, that if I draw a cross-sectional view for you, and this is my pile, this is pile cap, this is pile. If my section is, so our critical section lies at, yeah, so if this distance is, yeah, so if this distance is less than, here remember they have written d pile upon 2 because d by 2 is the critical distance, but I'm just wondering why they have not taken d pile cap. I would have assumed that this was the d effective depth of the pile cap and not pile, but anyway they have written pile over here. So if this section is closer to d pile upon 2, then you need not consider any shear, and if it is away from d pile upon 2, then you consider the shear in terms of the reaction on the pile. Okay, that is what is being told. Yes. Okay, good. Then the next question is from, so moving on, next question is from engineer Dinesh. He is a working professional from Tamil Nadu, and he is asking, I am designing a PEB structure as per IS 800 code. Actual concept of PEB is to use slender sections. If web is slender, stat calculates moment capacity, design is done. But if flange and web are slender, then in defined slender section, stat says slender members cannot be checked. But when we use the same sections in AISC, design is carried out and no warning sign is seen. How to design these? Very good. So if you have slender sections, in IS 800 2007, if you see, okay, if you look at the IS 800 2007, it allows us to use the slender webs in calculate in design. How is the issue of slender webs considered in the IS 800? IS 800 allows slender webs. How is it? How is the issue of slender webs considered in the calculation? That we ignore the webs from all our moment calculations. Okay, so that is how IS 800 consider use of slender webs. Now, if you look at slender flanges, IS 800 as of now does not allow you slender flanges. So if you provide slender flanges, then the code says that you need to go to IS 801, but then it stops over there and it does not tell you anything more than that. Now, if you look at the AISC code, AISC 360, AISC allows you the usage of slender webs are allowed, slender flanges are also allowed. For both the slender webs and slender flanges, what we have to do is we have to take the concept of effective width. So meaning of effective width is, let's say over here the flange is slender, then this, let's say this portion, whatever was leading to slender flange, this portion is ignored. Okay, in our calculations, and only this particular effective width will be considered. Similarly, if you have a slender web, how does AISC 360 deal with it? So this portion is ignored. The mid portion, where it is sort of unattached because the attachment was happening over here and here, so this portion will be ignored, and then the calculations will be done for the remaining width. So this is how your AISC 360 deals with the slenderness issues. This is the same concept of the effective width. As of now, IS 800 does not give you the effective width concept. It in turn tells you to go to IS 801. But then what is STAD doing? That STAD does not go to IS 801, and STAD straight away does not allow you to use the slender flanges. So slender webs it will consider, because IS 800 allows you to use slender webs. How to consider slender webs? By ignoring the web portion in your moment calculations. But if you have slender flanges, IS 800, because it does not allow you directly, it will uh, take you to the IS 801. But because IS 801 is, let's say, not integrated properly with STAD will not do the calculations. While in AISC 360, because it allows you to do the effective width method, the calculations will be accordingly done. So let's say if you have, okay, one more thing. Now, if you look at the NBC 2016, if you look at the NBC 2016, over there it has introduced the concept of effective widths for flanges also. Okay, so basically what has happened in NBC is that they have revised all the codes, and then they have given one uh, compilation of all the codes. So for example, IS 800 was last revised in 2007, but then there have been certain revisions that have been issued in NBC. So it is assumed that the structural engineers follow the NBC provisions, but nobody does so. STAD also does not do so. So then we are in a fix as of now what to do. So if I were just to take you to NBC, I have just taken that image right now. Are you able to see this image? So if you look at the NBC, it is allowing you the use of effective width method. So if you look over here, this is the figure from NBC right after the table which gives you the classification. So if your member is subjected to flexural compression, then it allows you to ignore this particular portion of the flange which was causing slenderness, and considering this much to be effective, and do the calculations for this. So you can follow this kind of a method if you want. Okay, you can use this kind of an approach if you want. STAD will not do this work for you. You will have to do it on your own. Okay. So having said that, what I will recommend you is that not to go for very slender flanges. What our IS code limits for slenderness, those are enough. I mean, do not try to go for slender flanges, because in our India we have all the other issues with quality control and on-site erection, installation, etc. And even if you go for this effective width method, it just gives you a 6-7%, 8% saving, or 6-7-8% improvement. So my suggestion to you would be not to go for slender flanges, because then there are other issues, and due to less quality control that is ensured on our Indian sites, better to not go for slender flanges and restrict ourselves to semi-compact flanges. uh, Better to restrict ourselves to semi-compact flanges. Okay, so these were my thoughts on your question. Good question that you asked. In our course on American steel design, we have done a detailed course on AISC 360. Over there, we have discussed all these issues and the calculations in great detail. So these were the questions that were asked on the Google form this week. Now we take up the questions from the live audience. So the first question is from engineer Vineet. He is a working professional from Patna. He is asking, after the discussion, please tell me the design of X-shaped column and its detailing at the cross junction. No, so I am assuming this is an RCC. What? I am assuming it's an RCC. Instead of X, maybe if this was a plus shaped column. No, so what do you mean design of? What do you mean by design of this column? For design, you need to do the normal approach that you have. You need the interaction diagram. Yeah, you need the PM interaction curve for this column design. So manually you won't be able to, let's say, calculate the PM diagram. So then in such a case, what you can do, you can go to your software like etabs, create this section in section designer. Okay, create this section in section designer, put the reinforcements, decide how you are going to place the reinforcement arrangement. You need to decide depending on this thickness, and I guess you can continue doing like this. At the junction, anyway, because it will be sort of a neutral axis, whichever bending moment direction you consider. So no need to put a lot of reinforcement in the junction as such. Just ensure that your sufficient reinforcement is there, so that when you are going to provide lateral ties, at that time you should have some reinforcement available over here. Beyond that, don't put much reinforcement in the junction, this cross junction, common junction as such. Okay, so then make a section designer, make this section on section designer, and then take the section, then take this column cross section to your software like etabs, do the analysis. It will check this cross section. Accordingly, it will give you the sufficiency of this section. So I think this type of a process you need to follow. So treat them as, let's say, multiple flanges of your wall. So as you would provide your reinforcement in wall, provide similar type of reinforcement in the junction. Just ensure that you are able to provide lateral ties in two principal directions like this. Otherwise, there is not much need to provide lot of longitudinal reinforcement in this junction. Just 4 bars at 4 corners of this junction are enough, and rest continue as a common reinforcement arrangement that you give. Okay, if you have any specific question related to this, please share some sketches or any diagrams if you have. Okay, then next question is from engineer Santosh Kumar. He is saying, I am designing a substation in UAE. The building is 80 meters long and 40 meters, an expansion joint at 40 meters. If we keep the entire model in one model, the base shear is more. If we separate, then it will be less. No, so what you can do is, let's say this was your portion 1, and here you have put an expansion joint. Okay, what you can do is, maybe what's happening, just first check what is the time period being calculated by the software. All right. So because in the American, I am assuming you are using ASC 7. uh, so ASC 7 does allow you to take the, it does allow you to consider the computer calculated time periods. That means the model time periods you can straight away take for Bayesian calculations. So first of all, check how the model shapes are being generated. Is this being considered in the software as a separate unit, and is this being considered as a separate unit? Check that first. If not, then what I can suggest you is that you make two models. In one model, you just model this. Okay, in second model you just model this. Then what you do, in those two models, you calculate the base shear, calculate the story level forces, then you bring them to your main model, where you have modeled both the 1 and 2 with the expansion joint. And then in the main model, you apply diaphragm, you apply one diaphragm over here, and another diaphragm has to be applied to your second portion. And then, using the user defined loads in EQ, you put your EQ forces at each story level that you had got from your individual model. So you understand? So you first made two separate models, you calculated the EQ time periods, and you calculated the base shear, you calculated the story level forces, note them down somewhere. Then you come to your main model, where you have modeled both the portions with the expansion joint. Then in this main model, you apply the story level forces that you brought from your individual models, and then you do the further calculations. Okay, so this is my suggestion for you. Then Vishali is asking, please explain about lateral torsional buckling. No, so that's a long discussion. What exactly do you want to understand? I mean, if lateral torsional buckling, I'll take almost 1 hour for explanation. Lateral torsional buckling as per table 16. Table 16 just gives you the appropriate effective lengths to be considered as LLT for your lateral dorsal buckling calculations. So the calculations that are given to you in Annexure E, I think, E or Annexure D of IS 800 2007, over there the effective lengths to be considered are to be taken from this table 16. So let me just open table 16 and try to recall what is given. Yeah, effective length for LLT for cantilevers. Yeah. So lateral torsional buckling is basically the effect of when your compression flange of a cross section, which is subjected to flexure, let's say moment is sagging in nature. So this is my compression flange. So this compression flange along its length will try to buckle. When this compression flange tries to buckle along the length, what happens, that because of buckling of only compression flange, this, let's say, undergoes buckling. Now because of this buckling, what happens is that this portion has buckled, but this portion elongates, the tension flange elongates. Now because of this type of an effect, in addition to buckling, there is a certain twisting of the cross section that happens. That twisting happens about the minor axis because the buckling is also taking place about the minor axis. So there is a mix of buckling, and with buckling there is an associated torsion. And because it is happening about the minor axis, or it is happening about the axis perpendicular to the axis of bending. So bending is, let's say, happening about the x-x axis, but the buckling is happening about the y-y axis, which is lateral to the x-x axis. So therefore we call it as the lateral. So the term evolves as lateral torsional buckling. Okay. Now if you look at the this table, it gives you the effective length to be considered for cantilevers, and it depends on the loading condition, whether your loading condition is adding to the effect of lateral torsional buckling or trying to I mean, when the loading condition adds to the effect of lateral torsional buckling, it is considered as destabilizing. Otherwise, it is considered as normal. And then you have the supports, how your cantilever is being supported, and then you have the conditions, how the what are the restraining conditions at the top flange. So on this basis, you are supposed to calculate the lateral torsional buckling length for cantilevers. Okay. So if you read the book on steel structure design by Professor Subramanian, his book uh, very well explains this concept. So you can read that book for further understanding. It will be helpful for you. Okay. All right. Good. So we have taken up all the queries. Any other query you have? Our live audience, do they have any other query? Because we have taken up all the queries that were put on the Google form, and from the live audience also. Okay, thank you. Okay, so I think there is no further query then. Thanks a lot for joining this session. Now, throughout the week, as you all know, that you can continue to put the queries on the Google form. The link for the form remains the same. And once every week when we meet, we take up your queries. So this is the link for the form. Yeah, so this is the link for the form. And if you want to connect with us directly on WhatsApp, then you can click on this link. So link for connecting with us directly on WhatsApp is this. So that's all for this session then. Thanks a lot for joining. And now we will meet you in the next session next weekend. Till then, have a good time and have a great week ahead. Bye bye. And thank you very much for joining today. Bye bye.